Recording in progress.
Wait, let me try to figure out how to unmute on my iPad instead. Oh, okay. Should be good now.
Okay.
Uh, maybe. Okay. So, I need a nice. Okay. So trigonometric identities. Oh my God. Okay, that's good. So, just go. Okay, so give me a sec. Yeah, I'll just go on here. So, introduction. Trigonometric identities uh, is a way we simplify expressions involving trigonometric functions that would otherwise be impossible to directly compute without a calculator. For instance, trigonometric identities can allow us to compute trigonometric functions evaluated at untraditional angles without a calculator. There's also going to be problems that ask you to prove a trigonometric identity, and you have to use previously known identities to simplify both sides. Purpose of this chapter is to familiarize ourselves with important identities. So these are some of the main identities. Uh, these two, let me annotate. These two are from the unit circle. If you have a unit circle and you have an angle x, and you draw its negative, which is basically going across, then its y value will be the opposite. If its cosine is going to be the same. Tangent is negative because tangent is sine over cosine. Um, and cotangent, cosecant, and secant are from sine, cosine, and tangent. These are the cotangent identities. You get them because when you draw this like here, it's gonna reflect across y equals x, and then you'll get like the previous x is equal to the new y. Uh, these are just this reflected. Okay, and then so here's some other basic identities. So this one, oh my god, this one is basically reflecting across the y axis. So point here will come here on the unit circle, and the sine is the same, but the cosine is negative. Tangent comes from sine over cosine. These are just reciprocals. Okay. And then here's an example. Yeah. So sine x plus pi over 2 is going to be sine of x plus 90 degrees. This is equal to, so x plus 90. We know that 90 minus x is good. So like circle. If this is x, x plus 90 will move you over here with a 90-degree rotation. And then you need the sine of the new one. The way to do this is you can realize that the sine here is equal to the sine of 180 minus x plus pi over 2. So it's equal to sine 80 minus 90 minus x, which is equal to sine 90 minus x, which is equal to cosine of x from our previous one. Okay. Shoot. Okay. You guys can try the next example.
Just cut off a little bit. If any of you guys have any question, you can talk to your lecturer and they can quickly answer your questions. So yeah. So if you have questions or you have any confusion about the procedures or the solutions, yeah, you can just ask. Oh, thank you, Vincent. Yeah, sorry.
You guys can try this. I'll give you like a minute to do this. I'll give you all like 30 more seconds, and if you have an answer, you can DM me. Okay, I'm gonna solve this now because it's been a bit. So first we know that tangent is sine over cosine. Secant is 1 over cosine. So tan over secant is equal to sine over cosine times cosine, which is equal to sine x. Okay. I think there might be. Okay, Pythagorean identities. So this basically follows from the Pythagorean theorem. If you want to know why, draw a unit circle again. Sine x is going to be the y, cos x is going to be the x. So, and this is a unit circle, so the hypotenuse is 1, just do the Pythagorean theorem. Okay. These can also follow from this. Does anyone know why? Okay. Wait, how do I do this? Does anyone want to explain how to get this? Uh, yeah, Alexander.
So this one we have 1 plus cosine squared x over sine x, and then which is equal to sine squared x, and then that's equal to sine squared x plus cosine x squared over sine x squared. So then that would be equal to 1 over sine x squared, which is cosecant x squared. The second one, basically we have sine x squared plus cosine x squared over cosine x squared, which is equal to secant x squared.
Yeah, that's correct. Good job. Okay. Yeah, those follow. You just from here you just divide by sine squared x for this one and divide by cos squared x for this one. All right. Cool. Okay. So, okay. All right. Okay. Sometimes there's gonna be more than one identity. Like there's gonna be algebraic identities that can help with simplification. For instance, difference of squares. So, anyone know how to simplify this?
Like sine x squared is equal to what 1 minus cosine x squared. Then like we do difference of squares, we do a little cancellation and we get cosine x plus 1.
Yeah, okay. So, you just, okay, so, okay. Yes, correct. You just, yeah, because you multiply by 1 plus cos x over 1 plus cos x. Once you multiply this to sine squared x over 1 minus cos x, difference of squares here, you get like 1 minus cos squared x, which is equal to sine x. And then everything cancels out, and then you're just left with this, which is much nicer. Okay. Next one, does anyone know how to do this problem? Or actually, you guys can take a minute to solve this and DM me once you get the correct answer. Oh, also, don't DM to my iPad because I can't see chats on there. Okay, I don't think anyone is doing this. I'll just go through the next one. I'll just go through this one. Okay. So how I do this, it's not nice seeing a bunch of different trigonometric functions. So you're gonna want to express them all in terms of sine and cosine. Simplify this because it's much messier. 1 over cosecant and 1 over sine x times 1 over cosine x. So you can move that to the is here. So you can move that to the denominator. You get 1 over 1 plus tan x. sine x cos x. This is sine over cosine, so the cosine can cancel out here, and you get cos x plus 1. So you're left with 1 over sine x times cosine x plus 1. You do basically the same thing as last time, I think. You do multiply by. Okay, so our goal is cotangent, which is cosine over sine. Yeah. Did I do something wrong? Oh shoot. This should be cosine plus sine. Yeah, my bad. So this should be cosine plus sine. What I did wrong. 1 over cosine. Yeah, okay. So we just need to show that cosine x is 1 over this ugly expression. Oh my bad. Okay, how do I do this? So okay, so you're gonna multiply by. Okay, wait. What am I doing? I guess you multiply this denominator out. Dude, is my pencil working? Oh, okay. Multiply this. So cos squared x plus. Okay, wait, I definitely did something wrong. My bad. Technical issues.
Wait, I think it's 1 plus tangent squared of x, not 1 plus tan x.
Oh my god, okay. Thank you. Alright, this makes it better. Let me restart. Alright. Clear all. Okay. 1 over sine times cosine times 1 plus tangent squared. We also saw tangent squared some other place. Should be over here. So 1 plus tangent squared is secant squared. So we can go back. Yeah, okay, yeah. Good. Wait, wrong problem. Okay, secant squared. This is secant squared. Yeah, that's true. So this is equal to 1 over sine times cosine. Wait, please don't draw. Preferably. Okay, it's 1 over sine times cosine. Secant squared is 1 over cosine squared. So cosine squared moves to the top, cosine squared. Cancel here. Cosine over sine, which is conveniently our cotangent x. Okay. Yeah, sorry, there was a typo. Okay. Next problem. Does anyone want to solve this? If you like get it, just DM me. I'll give you all like a minute to solve it, and please send it to my DMs. Actually, I think I have a better idea. I'm not gonna ask you guys to solve the question, but I will ask someone Okay. Does anyone have the first step to the problem? Someone that hasn't answered already. Okay. Yeah, you can answer.
Me?
Yeah.
So then you just combine the fractions. And then you get 1 plus sine x plus 1 minus sine x divided by 1 minus sine x times 1 plus sine x.
Okay, yeah, that's the first step. I'll just simplify the bottom. Okay, so using this, does anyone know how to get 2 times secant squared x?
So like 1 minus sine squared x is equal to cosine squared x, and then the numerator simplifies into 2.
Yeah, and then you just basically solve the problem because
And then it's 2 secant x squared by definition.
okay, yeah. So then this is equal to this because secant is the reciprocal of cosine. Okay, next topic. Oh, this is so messy. Let me clear my drawing. Alright, so sums and differences of angles. Sine of x plus y is sine x cos y plus cos x sine y. The way to memorize this is, okay, there's gonna be a plus in the middle. That you have to memorize, but for sine, it's gonna be sine x, and then a separate term will be cos x, and then it's gonna be alternating. Oh, sorry. And then for cosine, it's gonna be a minus sign. For sine is a plus sign. For cosine is a minus. For cosine, you're gonna write cosine, sine, sine, and then you can put in the arguments. Tangent is special. It's just memorization. Like, I guess you can derive it. Here is a chart, I think, of how to derive it. Basically, let me see this. So you have your triangle where this is 1. Let me clear my drawings. So your actual triangle is gonna be this. Let me change pen color as well. Okay, so your triangle is gonna be this triangle. This is your triangle where sine beta cos beta. This is gonna be beta. So you let this be alpha, and now you want to calculate the other stuff. You know that this bottom base is gonna be cos alpha cos beta based on this. And then this is sine alpha cos beta. You also know by similar triangles, this is also alpha. So you get these two side lengths. And then sine of this big angle is gonna be the y from here over the hypotenuse, which is conveniently 1. It's just this then. And the cosine is gonna be this whole thing minus this thing, which is where we get this. And then for the tangents, you just divide these two and get simplified. So next problem. Okay. Does anyone know how to do this? So okay, I'll split it up into sections. I'll give you guys a minute for computing sine 15 degrees. And again, send it to me on my computer. All right, so it's been a while. does anyone that hasn't answered yet, do they know how to do the first part? Just sine 15. Anyone? Okay.
If you use a formula, you get sine 45 times cosine 30 minus sine 30 times cosine 45 is equal to root 6 minus root 2 over 4.
Oh yeah, that's right. Okay. Yeah, okay. That's correct. So you just use the formula, you get sine 45 cosine. Okay, so this is negative 30, but or this is minus 30, but you can treat it as plus negative 30. So that's easier to use rules. So cos negative 30 plus cos 45 sine negative 30. You just plug in the values and then you'll get root 6 minus root 2 over 4, I believe. Okay. That's the first part. Clear my drawings. Does anyone know how to do sine 75? Somebody that hasn't answered. Actually, I'm gonna cold call. Hmm. Hmm. I'll give you guys a minute to think about it, though. Okay, does anyone want to raise their hand and answer sine 75? Someone that hasn't answered yet, because same kind of repetitive. Oh, okay. You know, I'll actually just do these because they're not that bad. Um I'll just demonstrate the rest. Okay, sine 75. Well, we just did 45 minus 30, 45 plus 30 now. You get sine 45 cos 30 plus cos 45 sine 30. And simplify this, you get root 6 plus root 2 over 4. For cosine 15, we have the same thing. So you can do cos 45 cos 30 plus sine 45 sine 40 because there's a minus. It's negative 30, so cosine negative 30 is cos 30. Sine negative 30 is negative sine 30, so the minus sign turns into a plus sign. So this is going to be equal to, eventually you'll get root 6 plus root 2 over 4. The last one, you just change the sign here and you get root 6 minus root 2 over 4. All right. Okay. Next problem. Oh, okay. Double angle formulas. So if we just set y is equal to x in the in our angle sum formulas, we get sine x cos x plus cos x sine x, which gives us this. All right. Cosine, same thing, and tangent, same thing. Yeah. Okay. In order to get this bottom part, deriving these is not that bad. You just do cos squared x minus sine squared x. And then you can add cos squared, and then you know that cos squared x plus sine squared x. Oh my god. Sine squared x is equal to 1. So you can add that and subtract it and subtract the 1 to get this, because that's cosine squared x plus cosine squared x plus sine squared x minus sine squared x minus 1, which is basically just this plus this minus this. Same thing for this. And then deriving these isn't that bad, but you have to be able to use these in an appropriate way, because it's sometimes better to use this one, sometimes it's better to use this one, and sometimes it's better to use this one. Okay. Next one. Anyone know how to do this one? Somebody that hasn't answered yet? Okay, I guess there's a... Okay, that's not what I'm going for. I don't want you to use something. This is possible with stuff that we've learned so far, I think. Okay, wait, let me try to do this actually. Okay, does anyone want to share what they think is the first step for this problem? Okay, I'll try to do this. Okay, so the first thing I think of, we just covered double angle. Why don't we get a double angle? So multiply by cos x minus sine x over itself onto this, so you get cos x minus sine x squared over cosine of 2x, which is equal to, well, this is cos squared plus sine squared minus 2 sine x cos x over cos 2x, which is 1 minus 2 sine, or it's, okay,
Yeah,
this is
1
sine
minus
2x.
2 times sine x.
It's 1 minus
Yeah, 1
sine
minus sine 2x, and then I think that's equal to like cosine
over
2x.
cos 2x. Yeah, I think that's how you simplify. I actually don't know what I was going for. Alright, there's less trigonometric functions, so I'm gonna say that's simplified. Okay, last thing. Oh my god. Is gonna be half angle identities. Okay, here you're just gonna plug in x over 2 as into your double angle. Cosine x is equal to 1 minus 2. Okay, so let me write this out. Cosine of 2x is equal to 1 minus 2 sine squared x. So if we turn this into an x over 2, well, then you're gonna get this is x. So cos x is equal to this. Isolate sine x over 2, and you get this expression. Same for cos x. Yeah, okay. Samuel, you can go now. Yeah. And if anyone has questions while we're on the second half, you can DM me. Yeah.
Okay, so can you start by making me the host?
Oh
'Cause
yeah.
that
Okay.
may or may not be useful.
But how do I give you host?
You just go to
Oh, here,
participate.
make host. Okay. Yeah, it should be the host now.
Let me see. Nope, I think you're still a host.
Oh, okay, wait. Let me stop share for now. Oh, okay, yeah, here.
Okay, so I'm gonna start by sharing the thing. Okay, so so this would be all right. So where Vincent left off was the half angle identities, which are just like the counterparts to the double angle identity. And so an immediate application of half angle identities would be computing cosine 15 yet another way. So in this case here, you could see that it's just really standard, except that the thing I want to point out would be the plus minus here. Because if you notice in like the half angle identities, there's these pair of plus minuses. So over here, usually you deal with the plus minuses by looking at which quadrant the angle is in. And like depending on which quadrant the angle is in, for instance, if we want to find cosine of an angle and that angle is in like this quadrant, then cosine would be negative. But if it's in this quadrant, then the cosine would be positive. So yeah, in this case here, cosine 15 definitely is in quadrant 1, so it would be positive. So you get cosine 15 is equal to root 6 plus root 2 over 4. Oh wait, no, is equal to square root of 2 plus root 3 over 4. And you can actually check that this thing, the square root of 2 plus root 3 over 4 is equal to root 6 plus root 2 over 4. And cosine 15 is like a really popular angle that is tested in trigonometry. So sometimes it's like better to like memorize some of these angles. This one is a little more nuanced. It's more complex, and I don't see it as often, but it's simply derived by just doing tangent of x over 2 is equal to sine of x over 2 over cosine of x over 2. So yeah, the proof of this, there's a lot of casework because if you could tell, there's like a plus minus and there's like a whole bunch of issues on like what the quadrant could be. So like I will not go over this, but yeah, you just know we have this thing right here. Okay, so we'll just look at a quick example real quick. So if sine of theta, we're given sine of theta is equal to 1/4, and we're asked to find cosine of 2 theta. So I would like just go over this because this is not a really difficult thing. So we just use the double angle identities. So you get 1 minus 2 sine squared theta, on which we just plug this in. And you get this to be what? 31 over 30. Oh, wait, no. Yeah. 7 over 8. Yeah, I think that's right. So yeah, that's an application of the double angle identities. Oh, and this one, the next one here is a really interesting one. So I will first give you some time to think about it. I will point out that if you observe these angles, 40 is twice of 20 and 80 is twice of 40. So it feels like it should be double angle. So, but like it's not there yet. So we're missing something. So I'll let you think about what that something we're missing is. And if you feel like you have something, feel free to let me know. Okay, so assuming you have had enough time to at least work this one through. So the idea is to recognize that, okay, so we have a product of cosines. And the idea is to use it's all the way up here. So sine of 2x is equal to 2 sine x cosine x. This is a product of trigonometric functions, except we have a sine. And we don't have a sine all the way. And we don't have a sign in this expression. So we need to somehow invent a sign into this equation. And the way to do this is, of course, to multiply the top by 20 degrees. And then like, yeah, multiply both the numerator and the denominator by 20 degrees. And now we see that we have a really interesting thing on the numerator. Because first you will look at these two terms and you realize that, oh, well, this is just the double angle for sine. So what this is equal to, this thing right here, this is just half of sine 40. So if we rewrite this, this would be half of sine 40, cosine 40, cosine 80 over the sine of 20. And now we can just repeat the process. we have a sine 40 and a cosine 40. This right here is equal to half of the sine of 80 degrees. So therefore, we can, again, simplify the equation. And now it becomes a fourth because we have half times a half of sine of 80 degrees times cosine of 80 degrees. And we can simplify this once more into 1/8 of the sine of 160 degrees over sine of 20 degrees. Okay, so this is still not fully simplified, but it's close. So if anyone sees
They're
the
equal.
last,
Like sine
Yeah.
160 is equal to sine of 20 degrees. Therefore, what we have is 1/8.
yes, exactly, because 160 degrees, if you just think about it, it's just 180 minus 20. So this is 160, this is 20. So yeah, the signs are equal, so they cancel. So this weird thing just becomes an eighth, which I think is pretty interesting. So yeah, that's like a really powerful application of double angle identities. Oh, and here is another example. These are the triple angle identities, and we're going to derive a formula for sine of 3x and cosine of 3x. So the idea behind this is, yeah, just write 3x in terms of 2x plus x. So because this is a show problem, I'll just go ahead and do it. Sine of 3x is equal to sine of 2x plus x. And let's see, this is equal to, I'll write it on the bottom. Sine. And these two guys right here, they're still not standard sine x, cosine x. So we use the double angle identities to deal with them real quick. Oops. Combine these two, and then this one right here becomes sine of x. And then for this one right here, we are going to use the version for sine because the question wants it completely in sine. So that's what we're going to do. So 1 minus 2 sine squared of x. And the last thing to take care of would be, of course, is cosine squared x. And that's where we have the Pythagorean identities. And then we just get something like this. We could simplify this right here, combine like terms. That isn't too hard. And yeah, there we have it. The cosine case is really similar. I don't have space, so let me see if I can.
Wait,
Yeah,
just-
it's really similar, so I'll just skip it.
Oh my god. Clear your drawing, and then it should be good.
Yeah, I think. Do we have time?
Yeah, that's good.
Yeah, I'll just like do that one as well, because like why not? Okay, so the cosine one is exactly the same, so nothing new going on here. This time you have to use the sum angle for cosine. And this one right here, we want to write everything in terms of cosine. So yeah. And once again, we have the sine squared x. We use Pythagorean identities to take care of that. Then we have combine like terms. And we should get something like this as desired. And speaking of which, there is a nice memoric trick that I find sometimes really useful if you don't if you sometimes forget like because like this identity right here, like the cosine angle sum identity and the sine angle sine identity could be sometimes it is easy to get mixed up and like stuff. So a nice trick to remember is that sine always keeps the sign. So sine of x plus y always keeps the sign. So this here will always be a positive. And if this is a negative, this right here will also be a negative. And then the terms right here, because you have a sine and like a cosine, just think of it as the opposite of plus. It's negative, it's reverse. So it's sine x cosine y minus or plus whatever, sine y or cosine x sine y. And then the cosine would be opposite signs because sine is the same sign. So cosine would be opposite signs. But then the cosine, like the trigonometric functions within would be the same. So cosine of x minus y, it would change the sign. So this would be a plus, and it would be cosine x cosine y plus sine x sine sine y. So yeah, that's just a nice memoric trick in case you get confused about these trigonometric identities, because there is a lot and it's easy to get messed up. So yeah, sine keeps the sign. Oh, and these guys here, these guys are even like harder to memorize, and I don't have a trick for them, but then they're really easy to derive. So the power of these identities, the product to sum, is that we could turn a product of trigonometric functions into a sum. And the idea is that sometimes when we have some weird angles here, like 17 degrees, or I don't know, like cosine, let me think one, like 13 degrees, then we can like apply something like this to turn it into something maybe that's more manageable. We have a sine of 4 degrees over here, and then we have plus sine of 30 degrees, and we know sine of 30 degrees is just half. So this right here could be useful in many scenarios like this that would be otherwise a little bit annoying. The proof of these require, again, the sum angle for sine and cosine. So I've assigned so these questions, the proof of these identities are as a challenge in the homework. It's not too hard. You just need to be practical with the details, and it's nice practice to see if you've memorized these identities, these sum angle and difference angle identities or not. These right here are just the converse. They're just these identities, but like you like rewrite them. And yeah, that's about it. And it allows us to turn a sum of angles into a product of angles, useful for the same reasons. Okay, so an example of the power behind these identities would be something like this. So 14 degrees and 46 degrees, that's bad. We don't know anything about these angles. But luckily for us, we have these identities, and we could turn the numerator into something we do know. It's twice of, let me think, sine of, I think 30 degrees, and then cosine of negative 16 degrees, if you apply those formulas. And then we have a cosine 16 on the bottom, so we divide that by cosine 16 degrees. And once again, these two cancel, because if you think about it from the unit circle perspective, this right here is 16 degrees. This right here is negative 16 degrees. So yeah, they have the same x coordinate, and therefore their cosines are the same. So yeah, this right here becomes what? Twice of sine 30 degrees, which is just 1. Okay, so that's the sum to product and product to sum. So that's pretty much about all the identities you need to know for the sake of precalculus. All the trig identities, that is. There are more if you're interested, but these are like the ones you definitely need to remember right here. They're just a review of what we've covered so far. And yeah, that's that. I just took a screenshot because I'm too lazy. So so yeah, without further ado, because we know all these trig identities and stuff, we can now move on to solving things like trig equations, which are, as you expected, just equations, but with trigonometric functions. So you have the equation with lots of trigonometric functions and whatnot. And to solve it, because it's not easy to have like when you have like sine x, cosine y, and a whole bunch of stuff, you want to use trig identities to simplify the equation and turn it into something you know how to solve. What's the things you know how to solve? Like sine theta is half. We know how to solve this. But then it might be hard to solve something like sine of, I don't know, theta over 2, cosine theta over 2 is equal to, I don't know, like 2. Like that's much harder to solve. So yeah. Oh, no, not 2. What am I doing? It should be 4th. So the idea behind these questions is to somehow rewrite the complicated trigonometric parts and rewrite them into something we know is more manageable. Also, it is really important to keep in mind that a lot of equations just say solve sine theta is half. And if you just write theta is equal to, I don't know, pi over 6, which is 30 degrees, this is not enough because we want to, whenever we solve a trig function, unless it is otherwise specified, it will have infinite solutions. So it could be 5 pi over 6 as well. And it could be any of these plus any multiple of 2k, of 2 pi, because the period of sine is 2 pi. So yeah. An example of this is this nice thing over here. We don't want to expand this with double angle. You just solve it. So yeah, as a practice, I will let you solve this to see if you get the hang of trig equations. So I'll give you around like 2 minutes to solve this. It shouldn't be too hard. So yeah, have a try at this. Oh, also I would like to point out that although it's acceptable to write these in radians, so like if you give the answer like this, so if you have 15 degrees plus this, well, directly this would be correct. It is best to avoid such notation, especially if you don't include a angle symbol on the top right here, because if you don't, that is just wrong, because we don't even know if it's assumed in degrees or radians or whatever. It's just wrong. So the idea is you want to convert all of these into either radians or either degrees. So yeah, for this question over here, the idea is we just solve sine x equals half first, which we know has solutions of, I'll use radians, pi over 6 plus 2k pi or 5 pi over 6 plus 2k pi. So yeah, you just divide this thing by 2 to get all possible solutions. Here, the k here, what the k means is that k could be any integer. For any integer of k, these two things will be a solution if you plug in any integer value of k. And the same goes for this. So that's what this notation means. K is a parameter, a dummy variable. You could replace the k with I. And you just got to write that this right here, it's I in theta. That's all this means. It's just some set notation and stuff. So a question like this, it's also pretty easy. I could give you guys like 2 minutes to think about it. Yeah, just be careful about like the pi in the equation. That could possibly lead to some interesting conversions between radians and stuff. Okay, so assuming you have had enough time to think about this. So the idea behind this question is really just you take a square root of 0 is 0. The only solution, like you just convert this equation to something like this. And let's just see when sine could be equal to 0. We know sine is 0 whenever sine is a multiple of pi. You could consider it again on the unit circle if you have any difficulties thinking of that. So k times pi, that is for any integer k. For the sake of it, I'll just not write that until the very end. So we first get rid of the pi over 4 on the left-hand side. And then we divide by pi. So we get that the answer turns out to be, I think this is right. Yeah. K minus a fourth for all integers. Well, again, to revisit this notation, this just means negative a fourth, negative 3/4, blah, blah, blah in this direction, and blah, blah, blah in that direction. Like negative 5/4, negative 1/4, 3/4, 7/4, so on. That's what that means. Okay, so this question would be one of the first ones when we have to use a trigonometric identity, because here we see that we actually have two trig functions, so it's not easy to solve it directly. So the idea behind this question, I'll just solve it, is it's just the double angle formula for cosine with a negative, of course. Okay.
Can you like use the fact that cosine squared x is equal to 1 minus sine squared of x?
Yes, that would also work, but you'll see that writing it like this instantly gives a solution. because, okay, if you would notice something, that is that the range of this function is between -1 and 1. But then you look at this side, we have cosine of 2x is -3/2. And something to notice is that -3/2 is not in this, it's not between -1 and 1. So therefore, there is no solutions to this trigonometric function, which is allowed. There's plenty of trig equations in which there are no solutions. So yeah, you could use Pythagorean, but then this right here just instantly, it's just like a instantly reveals that there's no solution to this equation. All right, so
The other one is like basically like we have 1 minus sine squared x plus sine squared x, which would give you 1 equals 3/2.
yes, this would be
No, wait, never mind. Yeah, I kind of messed up on that one. We have like 2 sine squared x is equal to 5/2. Sine squared x is 5/4, and either way, you find that it's wrong.
it's wrong. So yeah, either way works fine. You can use Pythagorean. A lot of times there are multiple, there's no one correct way unless the problem specifies use double angle identity. If it does not, you could use anything you want. And this question right here, there's no identity required. So I'll give you 2 minutes to think about this. It's not too difficult. Treat this as a quadratic. We have a cosine x squared, a cosine x minus 1. If you know how to solve something like 2y squared minus y minus 1 equals 0, then great. Just replace the y with cosine x and see what you would get.
Maybe here we can talk about like a Simon's trick, like, let the students to see if they know how to factorize it.
But then there aren't 2 variables, so you can't do that.
Oh, okay. I think you still can do it, right, with Simon's trick?
Wait, what
No,
is
SFFT is like for a 2 variable.
Yeah.
I think we can
You can, okay,
do this.
cosine x doesn't have to be an integer, so Simon's favorite factoring trick is mainly used when there's integers because there's gonna be a finite number of solutions. Here, if we did SFFT, it'd be really hard to get divisors. So
Oh, okay.
Okay, so the trick behind this question is that you can like factor. I'm sure everyone here knows how to factor. You just, or if you don't know how to like factor this, you could use the quadratic formula just the same. So you find that the solutions would be actually, because right here, what I've done is I've replaced cosine x with y. And when we replace this back, this would be cosine of x is either equal to -½ or 1. Does anyone have any questions with what I'm doing? If not, yeah, it's a really common trick. Sometimes you want to substitute for like if you want to simplify an expression down a bit. So yeah, you just solve this traditionally. You could get that x is equal to 0, 2 pi over 3, and 4 pi over 3. The question specifically says x is between 0 or 2 pi. So this case here, we don't need to add the plus k pi because these are the only solutions that are between 0 and 2 pi. I'm curious, is everyone familiar with interval notation? Yeah, I'll take that as a yes. So, because I think interval notation is like something that's really significant, especially when you move up to like calculus and stuff. Okay, so the next question, again, we have this thing, so we don't need to write plus k pi at the end or whatnot. So, okay, so for this one right here, we have several complex expressions on both sides. So the idea is we want to rewrite both sides of the equation to something more manageable. So let's start off with, let me see if I have another one. Yeah, so I'll just do this one. So we can start off with rewriting cosine of 2x and as twice of cosine squared x minus 1. The idea is that we want to return every single other trigonometric function in terms of cosine x. And once we do that, we can apply a similar technique up here because the only terms, the expression becomes simplified down to like the only expressions involving x are cosine of x. So therefore we can like treat that as one big whole, as a y, and then solve it like that. The idea behind using cosine x and not sine x is that the only instance of sine is in sine squared x. And we know by the Pythagorean identities that sine squared x is equal to 1 minus cosine squared x. And if you were to use sine instead, just look at this term and yeah, I don't think there's much you can do there. So I've said this right here, we could use the Pythagorean identities like this. So we have twice of 1 minus cosine squared x. All I have done is replace the stuff in the equation with the identities. Okay, so let's see. We have a 4 on this side, a -2. So move the -2, that's 6 cosine squared x. And then minus that thing goes there, so it's 9 cosine x. And then we have a 5 over here and a 2 over here. So it's plus 3. Okay, so now we can apply a similar technique. We can treat the cosine x as a whole. And we get something like this. Of course, first getting rid of the 3 that's on the right-hand side. So we divide both equations by 3, then we can factor it, or use a quadratic formula if you like. And yeah, we just have to solve cosine of x goes half or 1. And you can find that x must be 0, pi over 3, or 5 pi over 3. Does anyone have any questions with this? Because this technique is a pretty good one. It's like it could solve a lot of questions just like by rewriting complex functional equations, complex trigonometric equations into like stuff we do know, like cosine x in terms of cosine x or sine x, and then solving it as a whole in terms of cosine x or sine x. Okay, so if no one has any questions, I will now give you around 5 minutes to think about this question. There are two ways you can do this. You can either use the triple angle thing I found and then solve a cubic, which is bad, or you can think about that we have a sum of trigonometric functions. And is there identity that we could use that can convert a sum into something more useful? Because what is something particularly useful is when we have two numbers that multiply to 0, then we know that either A equals 0 or B equals 0. This is something that we definitely want. But so the question is, can we convert the left-hand side into something that is a product of two random terms? So I'll give you 5 minutes to think about this one. And if you have the answer, just let either me or Vincent know. Okay, so let's talk about how you would approach a question like this. So as I have alluded to before, we use the sum to product identities. We have a 0 on the right-hand side, and if we could get the left-hand side into a product of some terms, then we know that one of those terms must be equal to 0, and that gives us a lot of information. So using the sum to product identities, in particular, we're going to use sine of x, sine of y is equal to my sine of y over 2, and then cosine of x minus y over 2. I think this is correct. So applying this for x, Wait, is this right? Oh, wait, no, this is a plus. My bad. So applying this for y equals 3x, we can get that this will be 2 sine of 2x times cosine of negative x is equal to 0. Cosine of negative x is just cosine of x. So we get that either sine of 2x equals 0 or cosine of x equals 0. I hope this step makes sense, because to get a number that equals 0, to get a product of two numbers equal to 0, one of the numbers must be 0, or else how can the product be 0? So yeah, now we just solve this traditionally. Cosine of x has solutions pi over 2 plus k pi for an integer k. And this right here has solutions 2x equals pi times k for an integer k. So x would be k pi over 2. So we get that the solutions are x is equal to pi over 2 plus k pi, or k pi over 2, or k is an integer. Something to note here is that we can actually combine these two things here. So if we were to list out some of these solutions here, so we'll start off with this guy right over here. So if we plug in various values of k, we see that this right here is pi over 2, 3 pi over 2, 5 pi over 2, so on, so on. And if you were to list out these guys right over here, you get pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, so on. And what you notice here is that some of these guys are redundant. Pi over 2, pi over 2, 3 pi over 2, 3 pi over 2, 5 pi over 2, 5 pi over 2.
We could just describe it as k pi over 2.
Exactly. So the set of solutions in the first case is just a subset of the solutions in the second case. It is completely contained inside. So we can just rewrite this as x is equal to k pi over 2, where k is an integer. Yeah. So I think that's about it for trig equations. If there is anything you want us to go back through and go over again, feel free to ask. Or if there's something you just want me to re-explain, that's fine, and I can go back and re-explain it. So is there anything you guys want to go over again, or just see again at least?
Wait. So if class is 2 hours, then I think we can, yeah, let's talk about homework questions. Okay.
Yeah.
Okay, yeah. We can explain a few actually. I will wait, I can share. Okay, so should I go over the hardest or easiest questions?
Go over an easy one first.
Yeah, okay. Um, okay, honestly, I'm pretty sure most of the homework is not that bad. I have the homework PDF here.
Or do you want just like bring up additional questions? I could get that really quick.
I think we can do additional questions too.
I'll just do that.
Yeah, can you pull up some questions.
Real thing I feel like about trigonometric identities is if you just were to practice a lot, it just becomes more and more natural. Because no matter how much I talk, I could talk my mouth dry, and if you don't do any of the trigonometric equations, it would still be meaningless symbols on the page. So that's not the point. So I feel like doing the homework is really important. So I'll just go for some additional problems. I was like more practice.
Uh,
1 second. Uh, okay, sure. We have not talked about tangent yet, so I'll do that.
Oh yeah, you should probably derive tangent sum and stuff.
Can I add a page? Let me see.
Wait, I can open a whiteboard.
Oh no, it's fine. I could use this because I prefer using this. Whiteboard gets messy a lot.
Yeah, sure.
Okay, I'll just leave this thing real quick. 1 second.
I think you could just like derive tangent by taking like the sine sum over the cosine sum and then
Oh,
simplifying that a little.
Tangent half angle? Oh, that one's like,
No, like if you want to derive like tangent sum difference.
oh yeah, that's not too bad.
And for deriving tangent half angle, you could just use the tangent double angle formula and bash it a little.
Wait, actually, I think the tangent half angle shouldn't be that bad. Like, I do have a quick proof for both of them.
Sure. If you would like to,
Yeah, I can show that. Okay. Let me share.
I'll just stop sharing.
Yeah. Where is it? Week 2 slides. So I did disconnect my iPad, but I think I can still write fine. Yeah, annotate. So tan x over 2. We have our, oh my God, it is horrendous. Okay. Tan x over 2. We do have half angle identities over here. And then we can, oh shoot, wrong one. We do have we have half angles over here. If you divide these two, recall tangent is sine over cosine. If you do that, you get square root of 1 minus cos x over 1 plus cos x because of how square roots work. And then if you want to get, so you have, right now we have plus minus square root of, let's see, 1 minus cos x over 1 plus cos x. Okay, and then if you want to get like, hold up. So from here, if you want to get any of these two, then notice we already have 1 minus cos x. So if you multiply 1 minus cos x over 1 minus cos x, this becomes sine x squared. Sine x squared. And this becomes 1 minus cosine x squared. So when you take the square root, it becomes 1 minus cos x over sine x. And when you do that, 1 minus cos x and sin x, they're gonna like the sign will always be positive. Um, it's not that hard to prove. If you just go quadrant by quadrant, let's say in the grid, let's say here, then the tangent is gonna be positive in these two quadrants. And in these two quadrants, cosine 1 minus cosine is always positive. We know that. So it just depends on the sign of sine x. When the sign is positive, or actually no, 1 minus cos x. Oh yeah, but and then tan x over 2, if it's in these two quadrants, then the tangent is always gonna come back to the first quadrant. So anything above the x-axis will go to the first quadrant. Anything below the x-axis will go to the second quadrant. And because of that, we do know that the sine of tangent x will be equal to the sine of sine x, and that's good because tangent x over 2 should be positive when sine is positive and negative when sine is negative. Same for this. If you want to derive that, it might as well be easier from here because you already have the casework done. Let me clear this. Clear my drawings. You already have the casework done for this. You know that tan x over 2 is this established. You can multiply by 1 over cos x over, or 1 plus cos x over 1 plus cos x. In the bottom, you'll get 1 plus cos x times sine x. In the top, you'll get sine squared x. So then you just get that. Yeah. So tan x over 2, it has a okay proof. It's much harder than these proofs, but it's a lot simpler, which is good. Yeah. And then okay, we still have time. What do we do?
I'm just gonna like go over some random questions that I
Yeah,
find
sure.
are
You
pretty enlightening.
yeah, you can do
So
that.
do you guys want harder questions or easier questions? Because I feel like on the extreme end of the spectrum, there's questions that are really difficult, but then like that's probably not going to be tested on a standard pre-calc course in America. So I'll just go through some questions I feel like just
Wait,
aren't
you should do something that might help for the homework because the homework I think is kind of complicated. Like some questions.
yeah, let me see.
Cause like I made one question where you had to do conversions or not conversions like sine to cosine like that question.
I think kind of cosine. I think everyone.
Yeah, but like applications of that. Wait, actually I do have a question. I do have a question in mind. Let me make a whiteboard though, cause then we can like drag on problems. So okay, does
I'll just share my stuff. Like,
yeah okay, but yeah you can share your stuff.
it's some application things.
I do have a question though. Wait, you want to add your
Wait,
question?
I could just go over some general problem solving techniques.
Yeah, that's good. That's good.
Okay, so I'll just go over some general problem solving techniques. So because in the time we have, it's best it's more likely that we can get more high percentage.
Wait, also click follow my view.
Yeah. Wait, let me see how I do that. Yeah.
Go to the right top menu. Yeah, okay, that's good.
Okay, so there are a few problem solving techniques. So the one we've already seen is that when we have a complex expression that you do not know how to solve, the idea is that you a really common trope in questions is that you want to rewrite them in terms of sine or cosine. Because like extremely complicated high powers, it could be potentially, it's just really hard to solve because like how would you solve them? You typically want to uniformly like you want to turn an expression to something entirely of one variable. For example, we have something like sine 2x or cosine 2x, sine x. There's two variables. So there's technically two variables. We have a cosine 2x, sine of x. So we want to relate these two together and turn it into a one variable equation. You typically won't see equations involving x and y in standard trig classes. So that's usually a really general strategy. Second strategy is when you see something like sine squared of x, your mind should instantly tap into two things. It should be either can I just stick with sine x, or can I go with 1 minus cosine squared of x? Another common trope is when we have cosine squared of x, can I turn this into something like cosine 2x or vice versa? So you need to recognize the various forms of different trigonometric identities. Whenever we have something like 2 sine of x minus 1, you know we have 2 cosine squared x minus 1, you know you have to turn this into cosine of 2x. It's these type of things that could really help when simplifying trig identities. Another really important thing is converting between various angle types: sine, cosine, tangent, cosecant, secant, and cotangent. Because sometimes just a slight change from sine to cosine could unlock a whole new perspective on like this question and unlock like a whole bunch of potential identities that could be used. And of course, there's always wishful thinking. Like, when we have an expression equal to 0, can I turn this side into something like a times b? That way, either a is 0 or b is 0. And then, yeah, sometimes for the homework, if you don't know immediately how to solve it, try playing around and then try to get a sense of what the problem is about. And I think that's pretty much it. So that's some general problem solving techniques, I think.
I also have another problem solving technique.
Mhm.
So later on, like if you're doing geometry and you have something like trig stuff, like maybe trig like formulas, you're definitely gonna have a lot of like sine and sine stuff. Oh my God. You're gonna have a lot of trigonometric functions on the numerator and denominator. So actually I can just use text. So let's say you have like sine x, like I'm gonna make up numbers. Sine 40, cosine or sine 50, and maybe sine 10. So when you see these numbers and you also see some, and like let's say this is all in one numerator, right? So sine 40, sine 50, sine 10 is a horrendous product. You don't want it. But also at the same time, if you're gonna convert it into a sum, you're probably not gonna use product to sum. The way you do these types of problems is, um, you know, like 10, there's nothing that you can do to this, or there's nothing that will make another expression in here have a 10, like a 10 in their argument, except for I don't think sum to product. Yeah, I don't think sum to product will do it. Sorry, product to sum. But you do know one thing. Like when you let's consider these two terms. 40 and 50 add up to 90, which is nice because sine, oh my God, let me use text. Sine x times sine 90 minus x. You know this is equal to sine of x times cosine of x, and then you can use double angle formula. So this expression is actually equal to like sine 80, sorry, sine 80 over 2 times sine 10. And you can notice this for sine 80 and sine 10 as well. So this is one useful strategy when you're solving trig equations with a ton of fractions. Let me see. Is there anything else? You're gonna, when you have a bunch of products, you're gonna want it to telescope in some way, as in like you can keep canceling out terms until
I
you
think
get
that's
to
2x.
one eventual term. Yeah. But
I don't think that's ever like on standard pre-calc.
yeah, it might not be, but kind of helpful for like it's helpful for like
Yeah, in some-
simplifying huge products. Anything else?
yeah, I feel like pre-calc is more of finding, I don't know, sine of. So if you have like if there's a type of question, you have sine alpha equals something. You have thank you. You have sine alpha equals something. I'll just make them follow me.
Yeah, okay.
So if you have sine alpha equals something like this one, cosine of alpha equal and cosine of beta equals, or I don't know, tangent, that'd be better. Or I'll just stick with cosine equals something like 4/5. And then you're asked to compute a whole bunch of things. So they give that alpha is in quadrant 1. They give that cosine's in quadrant 4. And then you're asked to find things like cosine of alpha plus beta, stuff like that, or maybe tangent of, I don't know, alpha plus beta. And the idea here is just a thing that you have to be careful about, which is that the quadrant the angle is does matter. The first thing you want to do is to clearly find cosine of alpha, tangent of alpha, and so on, blah, blah. And then same thing for beta. You need to compute these values according to the quadrant. For instance, in this case, because beta is in the 4th quadrant, sine would be negative. So it's not 3/5, it's negative 3/5. And tangent would be negative 3/4. And once you get that basic deductions down, the rest just becomes a plug-in to the chug and plug into the identities. Another trope is the proof questions.
Shoot. Did he disconnect? That's wait, Samuel, do you have like okay, that's fine. Okay, I can okay, what was he talking about? He was talking about how I asked you to compute a bunch of stuff. Uh, what else should we explain? Is there any questions about like any of this right now? Okay, well, okay, so proof questions. Like, let's say you have some complicated expression here, and you have exactly one single trig function here. So this complicated expression with like maybe a fraction as well is equal to like sine x. So it's logically it's gonna make sense to okay, wait, let me follow. Logically, it's gonna make sense that you're gonna try to simplify the extremely complicated side. Like you should never ever work with both sides because that means you're not solving the problem. Because if you work with both sides, it means you already assume that this equality is true. And you're trying to prove that it's true. If you're using the fact that it's true to prove the question, then it's not a valid proof. So in most of the identities I was proving today, you should usually stick with the more complicated side and then try to shape that into the other side. There's also some other kinds of problems where it gives you complicated stuff on both sides, like this. So you're gonna try to meet in the middle. You're gonna simplify both sides. So you're gonna start from this side and simplify it until you get something nice, like maybe as an example 10x. And then you're gonna try to simplify, and now you have another equation you're trying to prove, and you try to prove it. And you're usually gonna apply some identities. If you see that it looks like an identity, then you might want to try using that identity to simplify it. But sometimes it's gonna have to require intermediate steps. What else? Okay. And also in the trigonometry part, I think teachers are probably just gonna want you to memorize that the unit circle and the few special values like 30, 45, 60, 90, and so on around the circle. These are some special values you should memorize. What else? Whenever you see a complicated expression and you see double angles, like let's say sine x, cos x, cos 2x, minus sine x, sine 2x. It's not helpful to expand the whole thing because that takes a ton of time. Expanding it gives you a bunch of quadratic stuff, which is not nice. See if you can apply some theorem that makes the question nicer. If you really have to, you can just if you really have to make it more complicated, you can do that. But you're generally gonna try to make make one of the sides nicer and nicer. You never want to make it messy. For example, like don't expand anything you see. Yeah, that's one thing. What else? If you see 1 plus or minus cos or sine x and it's in like a denominator or something, you can do if it's in like a denominator and there's some stuff above it like that includes sine x, then you can multiply by 1 with the opposite sign of cos x and then multiply by this over itself. So messy. Let me erase some stuff. Okay, never mind. Like let's say there's 1 plus minus cos x and it's in a fraction. You're generally gonna want to turn this into 1 minus cos squared x. Same for sine, because Pythagorean identities simplify it a lot, and those are nice. Yeah. And another thing, using the unit circle is very important. It's how you prove many identities, including Pythagorean. I think you can do some with this potentially. Yeah. Anything else? Anyone have any final questions that they would like to ask? Okay, if no more questions, I don't think there's any more topics. Okay, well, thank you for attending. I'm gonna post homework on Google Classroom cause we made some problems. And office hours on Wednesday? Okay. So, if you have questions about the homework, just attend office hours. Okay. Thank you all for attending class. Yeah. Have a nice evening. Yeah. Thank you. Wait, I still have to end the recording. Do you know how to end the recording? Cause wait, who's
I'm right, you should host.
oh yeah.
Guys,
Uh wait, Amber, can you close the recording because you're host?
Oh, wait, is this something you do? Oh.
Oh, I think only host can close the recording.
Oh, okay. I'll just stop the recording.